So, hello everybody. To the next session here, so JCon Europe. I'm going to talk about vector databases, what comes out of GPT now. And yeah, let's just jump into this. First of all, some words about me. I'm Erik Bamberg, software engineer, 20 years experience with Java, musician, indie maker, AIMM explorer. In my spare time, always open for new challenges, as you can see. And yeah, vector databases to learn everything about this was one of my challenges that I did this year. And I did a lot of talks over this year about this topic. And so I hope you will join it. Usually when you're in such a conference and your manager gave you the day off, or you are coming back to your wife, usually you got a question, oh, how was the conference? What did you learn today? Most of the time you say something like, well, I learned about this web framework, how to build a website more nicely. And you could ask, oh, didn't you do this on the last conference? And you say, oh, yeah, well, but yeah, no. But what we are doing today is I want to show you something. We want to today learn something about vector similarity search in a high-dimensional vector space. This sounds pretty cool, doesn't it? Vector similarity search in a high-dimensional vector space. And I hope that at the end of the talk, you will know everything about this term, so what means vector, what means similarity search, and how you do a vector similarity search in a vector space, even if it is high-dimensional. I hope that we will cover this all today in the session, and at the end of the session, you can, pretty sure, answer me this question. We will see. I will ask you this afterwards if you really have learned this. ChatGPT. Usually I ask the question now, who use ChatGPT in your company already, who works with ChatGPT? Found out a few people begin, or many companies begin now to really use ChatGPT. Usually I ask them about the challenges about ChatGPT. What's the problem with ChatGPT when they're using it? I get a few answers usually back. First is how people to overcome the token limitation that we have in ChatGPT nowadays. This is one really limitation on ChatGPT. It's getting better now. I think ChatGPT 3.5, we had 4,600 tokens maximum. Now we are at 32,000 tokens, up to 40,000 now, and it's getting more and more. Just learned last week that the even next model is even more. So we have a limitation of the tokens. If you think about even 40,000 tokens in ChatGPT, if I pick up a book from Harry Potter, first book, and I asked them, or the second book, I asked them about ChatGPT about, well, take this book and tell me everything about spiders in the book. 40,000 tokens is roughly enough to cover, let's say, 50 pages of a Harry Potter book. So the 50 first pages of Harry Potter, you usually don't have anything about spiders, so it will not be able to answer this question. The other point is of course your data that you have on your premise. ChatGPT does not know this data on your premise, so you have to find a way how you bring your data into ChatGPT in a most efficient way that ChatGPT can work with. So we see there were a lot of limitations about ChatGPT. Maybe I will cover later on this limitation again and see how we can solve this by using a new technology that I want to show you today. ChatGPT is definitely a hype topic. At the moment, everyone tries to use it. Everyone tries to get used to ChatGPT. But when I look into my newsletters and I see what's going on in the IT world, of course, ChatGPT is one topic, but there's another topic that's jumped in my mind over this year. There were a few companies that makes a lot of funding money at the moment. There's Pinecone is still 700 million Series B funding. Chroma, 80 million seed funding. A company open source called Weaviate, they make 50 million Series B funding this year. Malware 60 million Series A funding that they get. That comes up in my newsletter, and I was thinking, well, if this company is getting so much funding, what are they doing? They must something very interesting and very exciting for the future of all of us that these companies are doing, that they get such a high funding nowadays. So I did my research, of course, and I looked into this, and I found out that all those companies are doing one and the own thing, one and the same thing. And what they are doing is they're building vector databases. Actually, they are all working on vector database. Chroma is very new. The other ones a little bit longer on the market now. So I thought of myself, what is a vector database? How can I utilize this for myself? And yeah, what is this all about? Why do we need another kind of databases? If you look into the categories of databases that we have nowadays, I must get clear. We have already relational databases, Oracle, MySQL, name it. They are pretty good for structured data, ad hoc queries, transactional, all this transactional stuff you need transaction. This is the way to go for yourself. Then we have, of course, NoSQL databases. If you really have the requirement to scale out your databases, you probably will go for a NoSQL database like MongoDB, for example. They are key value based, document based, and scale out pretty good horizontally, and absolutely great for such tasks. We have graph database on Neo4j, complex relationship, hierarchical networks. You can all store this in graph databases, query this. Brilliant for this job. And now we have another one. We have vector databases, and this vector database covered one thing that all of the three other databases are not able to cover. And vector data covers the topic of unstructured data and semantic search. All the data that we have before, the relational databases, NoSQL database, Graph database, they were in any kind structured data that you have there. None of this database is really good in storing unstructured data and doing a semantic search on this unstructured data. So let's look what this actually means, unstructured data. So it's quite simple. Unstructured data is around 80%, so that's why it's important, of the data that we have nowadays, and content in internet or also in your company is kind of unstructured data. Unstructured data is everything like a video, an image, of course. Audio files can be unstructured data, or if you look in your company, how many PDFs and document files you have lying around stored on some servers, which is actually all data. And this is data you have to manage, you have to search in, you have to find the semantic of this, bring the information out of this together, store this in the database. So this is actually unstructured data, and we have a lot of this. I said 80% of all the data that we have nowadays is unstructured, and so it's hard to actually save this data. Usually how we are doing it, we are storing this in a blob in a database, the PDF file, an image, for example, we are storing in a database, and we are tagging it nowadays. We say, well, this is a video, and we tag it with, it's a video of cat, and it's a cute cat, and the cat is playing. So we do some human approach. We are just tagging it. It saves the tags along with the binary file with a blob inside of the database. This comes, of course, with a big problem. Have a look onto these images. Take a minute for yourself. To tag the both images. How would you tag this if you want to store this in a database? What are the correct tags for these images that you would store? Just think about it for a moment. Actually, I did my decision, and I'm pretty sure my decision might be a little bit different to what you did on your decision. For the left cat, I would say isn't cat. Well, for the white picture, I maybe would also tag it with a cat. It isn't cat, yeah. Orange is a orange brown. I maybe would tag it because it's the main color in it. You might say the left one is a cute cat, the white one is wild. In my opinion, also this tiger looks very cute. So I would probably also tag it with cute. If you have a lot of people in the team doing this tagging, you will find out that everyone have another opinion about the world of this image, and everyone will tag it different. So it makes it very hard to search for this data and to find something that is also a cute cat or awesome brown picture. And it's very hard because people are tagging this quite differently. And this is, of course, a problem. Every time nowadays we have such a complex problem, there is some solution that we have for this. One tooling nowadays is machine learning. usually we say it's hard to tag, it's hard to work with this. Can we have a model that's doing this for us? Can we put a model in between and this is doing the work for us? Yeah, of course we can do this in this. There were a lot of models nowadays that we can use to doing this tagging for ourselves. How this works is we are put in an image like this doc or an PDF or an audio file, whatever you have there is unstructured. You put it in a model. The model is trained on a lot of these images or documents and everything like this, and learn how they belongs to each other in a semantical way. And what we get out of this is an embedding, which is a multi-dimensional vector. That means we have an array of a lot of float point, which are representing our images in a space. So usually we will have an embedding of, let's say, 512 float points, maybe 768 float points, maybe more, maybe less. But the point is we have an unstructured data, we put it into a model, and what we get out of this is a vector embedding, which actually represents our object in this embedding. And we can do this with everything that we have, with words, with sentences, with images, with videos, with audio. For all of this kind of unstructured data, we nowadays will find common embeddings models which are already pre-trained. We can use this out of the box. Maybe need some transfer learning on this one to train this on our domain language, of course. But we have pre-trained models that work pretty good for many kind of unstructured data, like vision, like videos, vision, things like images, ResNet, AlexNet, for example, DanceNet. For text, we can use Bird, Tissily, Bird, GPT, everything like this. For audio, we have Wave2Vec, MX Audio. Source code, I just came across this on a project where I thought, oh, can I vectorize and embed to create an embedding of source code? And actually, yeah, there is Code2Vec and Code2Seek, and which are models where really you can put in a Java code and Python code, and it creates you and context-sensitive embedding, multidimensional array of source code. And you can do this. So the concept is the same for all the things. We have a model, we put in the unstructured data, and what we get out of this is such an embedding. And the cool thing with this embedding, it does make it so powerful, and why we can use it for the vector databases, is that this embeddings contains some contents, some context inside of this, semantical context inside of this. So usually on the left side, you see you have some New York, USA, Japan, Tokyo. And during the training process, this model actually learned the context, how things like words belong to each other. So they learned that New York and USA, you see on the left side, are close to each other because New York and USA is in the same country. And you have Tokyo and Japan, they belong somehow together. And you see another dimension. This is the yellow line there that shows you that also New York and Tokyo is in a dimension on the y-axis a little bit higher because they are all cities. Lower y-axis you have, USA, Japan, they are countries. But you see that the context of these are countries, these are cities, and these are city in countries belong to each other, so they are close in some way together and things. So you can do this for everything. Let's say we have our cute cat picture. Cute cat will be very similar to a tiger in the embedding. A black cat will also be a monkey will be close to the tiger, but not so much to is a cat. But you will see that then other contexts like bananas or trees, they are not animals, but they will belong a little bit close to monkeys. So this will be represented in a vector space in the sun. They will be together. Let's just jump out of the slides and visualize this. Google did a fantastic job here where do I have my things? Here I have. Google did in the lab 7 years ago, a fantastic job to create visualization tool. This is, by the way, it's not a vector database. This is just visualization of such an embedding model that they have. And this might help us to understand how this embedding works, and later on, how a vector database works in this space. You see, every point here that we see on our screen actually is a word, and we use a word embedding to create this. We see they all have multidimensional, So we see they are all floating around in a three-dimensional space. Of course, this is usually more dimensional space, but we are calculating it down. All these are words. I can just look for something. Let's say I look for the word king, for example. I say, oh, I got a word king here. Let's see this 100. And I see, let's say the next 10 words with the model things are quite similar to a king. Let me isolate these points so that I see. We will see that a king, the model we found that's usually queen is very close in words to a king. They always belongs together in a context thing. Throne, emperor, there's also words that belongs together to a king. Henry, the prince, that all be together in a context thing. So they are very, very close to each other in this vector space. When I'm searching here for cat, for example, believe me, you will not find it. It will be far, far away from a king. But cat and a tiger again will be close to each other. So I think this is a good representation so that we have to keep in mind if you're talking about vector databases now and what we can do with this vector databases. The visualization, I think the point is clear. You're using a model to get unstructured data in such a vector space, and everything that somehow belongs together, where the model had learned in a domain that it belongs together, will be in this vector space together. That means their embedding will be similar to each other. Let's see where we've been here. Don't know why I stopped my Q&A slideshow, but here we are again. This was a representation of high-dimensional vector. Now the question is what we can do with this and what have this all to do with vector databases. When we have this representation as high-dimensional vector spaces, what we can do then, we can use this data that's stored somewhere, all this data that we have there, to do some kind of a semantic search. That means if we have all these words or pictures that are in such a space, you see that the relevant document is the blue arrows, and we want to search for such an entry in the database, and we have something else which looks similar to what we are searching. We're looking for something which is similar to what we have. What we can do, of course, is we can have the thing that we are looking for, the document that we want to upload, for example, and we want to see if some similar document already uploaded and deduplicated, for example. And when we are uploading it, we can create in the same way as we're storing the data, we can create this embedding, and we are saying, look inside of this vector space, if this embedding from the query object that we have, if there are any objects which are close to this one, and this is the object that are usually similar to our object. This is what we want to get out of this. I will show some. I think I will show some examples on this later on. For example, if you have some pictures in this vector space, and we can have a third picture, and we are pulling in, we can search for this one. The good thing with this is we can combine this embedding. We can have, for example, in the same vector space, in the same data that we're creating, we can have models that are trained on doing the same embedding and bringing it together for text and images, for example. And this means it does not necessarily have to be that one embedding always representing an image and a vector. It can also be that we have embeddings in the same vector space with text, others are images, and we have trained the model so that the text embedding that we have are close to image embedding. And if you do so, we can have such really fancy things like we can do something like a text to image transformation by having a text like dogs in the snow, for example. We are creating an embedding for this, and we have images in our databases of dogs and cats and whatever we have, and we are using the embedding for dogs in the snow for the text, and looking inside of a database for any embedding on image which had an embedding which is quite close to our text dogs in the snow. And if we found it, we very probably will find an image back which represent our docs in slow. You can do this for Eiffel Tower by night. I did some tests with Eiffel Tower by night and have pictures of Eiffel Tower by day. So they are close to each other, but yeah, you will find an Eiffel Tower by night by passing in Eiffel Tower by night and so on. So what means that they are similar to each other? For a computer, this is quite simple to calculate and to get out. We're talking here about a vector similarity. So if you have this cat and a tiger, and we have an embedding of this, this is in a multidimensional space, and we have to find out which of this point or the embeddings are in the space close to each other. This is something that is pretty simple and easy to do. We have mathematics for this for many, many years. We have cosine similarity or Euclidean and Jacquard, for example, which are mathematical formulas. Helps us. You put in one multi-dimensional array of float points and another multi-dimensional array of float point. And the result of this mathematical function is always the distance between the two of them. So you have a distance of 1, which is far away, and you have 0.5, which is closer to each other. You have 0.2, which is even closer to each other. So you can use such mathematical format to find which of these vectors are actually similar to each other. That's just the theoretics about this. When we have this data, we have our image of a cat, for example, we are creating an embedding on top of this, then of course it would make sense in many cases that we have also some structured data that goes along with this data. Usually if I have a photograph and I know there's a title of this with Weaviate cat, I know I took this photograph in the year 2016, and the photographer, or I'm not Antwerp, but as is Antwerp, that did these things. So we usually want to store some information aside with this embedding somewhere. So we have some kind of combined data usually that says we have an embedding which represents our object, and we can have some structured data as well. And when we have such an, let's call it object, the question is what we do with this. Of course, we want to store it. We can take such an object, which is an embedding, which is structured data. We store it into a database. And by doing so, we have now the chance to doing a lot of query statements. We can really select in the database for pictures where this picture that I'm looking for is similar to another picture that I give in. I have another picture, I create an embedding and say, give me from the database the data sets which is a similar picture to what I put in. So if I put in a cat, I will very probably get back a picture of a tiger or a cat, maybe more a tiger than a cat. And I can add this also in query statements. If I put this information in a database, and I can say, select a picture that looks similar to another picture that I have here, or select all documents that look similar to a PDF document that a user just want to upload. And you can add also some metadata and say, and the photograph is and the doc type is like PDF and docs. And you can then query your database for, say, if you have objects similar to this. This helps you, for example, document duplication. Someone uploading a document PDF, and you're looking into your vector database and say, do I have with an object with similar embeddings that I did here? And you see how close they are to another. And then you can ask the user, oh, I have another document which looks quite exactly to what you wanted to upload here, a little bit different. But is this maybe a duplicate? Do you really want to upload it? Or you can use it for batch jobs that are doing the same thing in an automatical way. For everything like this, you need something like a database. You store the information that you already had as embeddings at this vector representation that you have. And then the vector database gives you the ability to select on top of this data to see, I have an object, give me every object that you have in a database, which is similar to this. And you can say, what means similar to me, how far they can maximum be away from each other. You can use this actually for many things, and I will give you later on a few examples or for use cases where we can use this, for example, to improve ChatGPT then. So actually, it's the main concept of the vector database. This is what vector databases do. A lot of theory now, I know. I tried this, I read this, and I tried this, and I was thinking, well, how fast can this be? Yeah. Well, how fast can it be? Why didn't I just implement it by myself and having a list of data and just using a Gaussian similarity function? There are a lot in libraries for Java, for Python, and everything. And I just iterate to my list of object data and do this on my own. Why should I do this? And I tried this vector databases, and I was really surprised because the vector databases are very, very, very fast. If you look into a vector database on Malware, for example, they are testing it with trillions of embeddings inside of the vector databases, and they got results in milliseconds, something like this. I guess they are pronounced. I tested it also storing not trillions. I don't have this space at home, but I tried this with really a lot of thousands of data, 50,000, 100,000 of data embeddings inside of the database in a small computer, and I asked him, query for give me the 5 data with quite similar pictures that you have, that are quite similar to my picture that I have here. And I think, okay, now I go on and make a T. Oh, no, it is finished. Actually, even if you're a big data size and you're looking for some similarity inside, this vector database are really able to give you the result in milliseconds, actually really in milliseconds. And they really can also scale out horizontal and everything that you expected from databases. Nowadays, they can do it. And this is really, really fast. And this was really impressive to me. When I saw this first, I was like, wow, this is something I have to look deeper into how this works. How can this be so fast? And let's find some use cases where I need the speed and what I can do with this. Yeah. First of all, the words of attention. These databases are fast because they're doing a little bit of tricks behind. One trick is, of course, from the vector databases, and that's something you really have to be aware of if you really decide to work with this, is that the vector databases actually don't give you the exact 10 results which are exactly closest to the point that you're looking for, but with a query. How they can be fast is first they're doing it in memory, another trick. But one trick is, of course, they're using an algorithm that calls approximate nearest neighbor search. That means they are not exactly giving you the 10 closest, but they're giving you which are probably very near to the neighbors. It is not guaranteed that they're really closest to what you are, but it is close enough for most cases that we have. And the other thing is all those vector databases uses something like indexing, of course, to index also data. HMSW is something very popular for this when these vector databases are using. So this refers to when you are trying to build it on your own, is they are holding some indexes, which, for example, just have, in this case here, 2 vectors, and you're looking for your search vector, say, which is similar to my vector. And this vector database really looks and first in 2 vectors and say, okay, your one is closest to the one on the left top edge of the 2. And then they're going down a layer, looking into another layer, and then they have a few more embeddings and say, oh, I'm on the left top, which one is closer to this one here? And they're going down layer by layer and finally get a result to you, which is very approximate the nearest data that you will find. So this is the way how these databases work and how these databases can be really, really fast. And in all my experiences I have so far with the databases, they are really, really fast. This absolutely is the case. If you want to try some of this, if there's something that you think, oh, makes sense to me, I can find a use case for this and use this in my own space. There were a few vector databases on the market at the moment for very interesting. I've just picked out a few of them. There is one, Pinecone. Everyone talking about Pinecone at the moment. This one is pretty good, pretty new, but pretty good. It's just cloud-based, unfortunately. You cannot host it on premise, on your own premise. So this might get a little bit costly if you use this. If you look into vector databases, there's another one, Weaviate, which I personally use a lot. It is an open source database, and you can also have a pro version of this, which provides a little bit more feature. They also have a cloud, but Weaviate is open source. You can host it on premise on your company computers where you are, and you host it and you have all under control. It's very, very mature. And Chroma DB have a nice, easy API. If we want to look into this, it's quite new. They just started building it, so it is not really mature, but I think it's promising over the time. This will make its way up to the top. Of course, Milvus is another one which I know, which is pretty good. It scales out pretty well, having very good architecture, in my opinion. It's one of the most advanced vector databases outside. If you do not want to jump into a new vector database, maybe you have already in your company systems like Redis. A lot of us have Redis, or a lot of us have also PostgreSQL in their company and using this. For this solutions like Redis and PostgreSQL, for example, there exist extensions that you can install of this, which actually give you a similar experience. You put it on top of Redis, and they give you a similarity search where you can say, I store here embeddings, search for it. The same exists for Postgres, where you can do this. It will not give you the same experience with a real vector database. For example, Weaviate have some thing like you can look for the 10 documents which are similar to your question, and then it can take the results of this and automatically take this result and push this result to ChatGPT with a prompt attached to it and say, oh, this is the predefined results that I found. Use the generative AI and summarize this in a little text for me. I will come to this in my use cases later on, but this is experience that you get from vector databases as well, which you usually will not get from this Redis PostgreSQL databases. But if you have this already, you want to take your first step in your company with this one, actually just give it a try. My click took some time. As I said, with Weaviate, just want to show a little bit how this works. You usually have a storage in those databases. You have a backend, as usually with databases, and you have a client. There's some code that can store code inside of your databases. And usually you have then two options that you can choose from. First option is you bring your own model into this, so you can host on-premise your own model, or even have it in your own virtual machine or in your own Python code that you are just running a model and you're creating your own embeddings and say, Weaviate, okay, I have an embedding and embedded data, store this for me. Or you can just say, database, I have an image here. And before this, you have configured what the database will do with images, what they do with text, what they do with videos, and which endpoint they should use to create these embeddings. And usually you can configure them, for example, Weaviate with adapters, and you say, whenever you get in an text, then call OpenAI and use a model hosted at OpenAI to get a text embedding for this. Or you can configure Hugging Face and say you have a hosted model running on Hugging Face, and you say, I need a text-to-vector encoding to get my embedding. You just save a text into Weaviate, and this database will automatically call Hugging Faces, doing the embeddings for you, and then push it to store. The same for queries. You're just querying it by put in an image or put in a text, and it will automatically create the embeddings for this. What are the use cases for this? Very, very shortly in top of this. I know this was very, very theoretical about how the databases work, and you might think, okay, that's great, a lot of mathematics, a lot of things that I learned, but what do I do with this? To store some cat pictures? Is this really what I want to do? No, their use cases are endless. You can have a lot of use cases with using vector databases. One, for example, is intruder detection system is one use case I found out here. So this is nothing new that we do in machine learning. You have some data from your network traffic, how long sessions are, how many packages, everything like this. You put it usually in a classification model and say, this is trained, this data represent an SQL injection attack. This is a normal behavior. This is another kind of attack. You classify this, and if you see new data, you check this with a prediction with a model, and this get a glass out of this a normal behavior or is an attack. Usually you can do this with a classification model, but yeah, you can do it also with a classification model with AutoSat, and you can create an embedding from this data, and you store this in a vector database, and you just new traffic comes and you're querying it from the vector database. Why that, you will ask? I have this model. Yeah, but the problem is every time you get new data in this new kind of injection and attacks, you have to retrain your model. You get more classes maybe, or you have to retrain because the circumstances changes. A vector database actually can store data, update and delete data. So you no need to retrain a model. You just delete data without obsolete and update data and store new embeddings, and you're done with this, and you can create new classification as you like. Face similarity, if you wanted to in similarity search, and someone will look like in telemetry a kind of app, or you have an end-to-end control in your company, look in a camera, oh, this is you are allowed to enter. You can use this, you can use vector databases as well with this. Another very interesting thing is now going to ChatGPT. This is something called retrieval augmented generation, RAG, at the moment. This is a technique that is widely used nowadays, and you can do. Usually ChatGPT had this token limits. I told you before. You have token limits for the data that you can push. You have to upload your data. You have a big product catalog. Do you really want to upload the whole product catalog to ChatGPT? Obviously not. You can use vector databases as a long-term memory for ChatGPT and or to help them to get your company data to ChatGPT. By doing this is you take all the data that you have in your company, like all the docs that you want to ask ChatGPT something about, and you chunk this in small pieces, and you create embeddings out of this. Small pieces might be paragraphs and so on, and you store these embeddings in a database. What you can do then is, if a user question comes in, you can ask this with some question answering with the machine learning, of course. You can ask the vector databases then, this is a user question. Please give me the 20 or the 50 paragraphs or document chunks that I stored before with the name of the documents, everything like this, which very probably will have the information that answers this user question. And when you get this back, you can put this all into a prompt and say, this is the data that I have. They're just limited to the 50 that you found, not to 10,000, 20,000. You just give the chunks of data, which you already know this is the data which probably can answer the question. And then you ask ChatGPT, and now answer this question from the user on top of this data that I just showed you. And this will help you also the ChatGPT hallucination that you have. ChatGPT, oh, I think I know this. It is a planet. That's absolutely true what I told you, but it's not because you don't have the data. With this approach, you can limitate this by just giving the data which have the information to ChatGPT. Weaviate and other databases have usually some built-in support for these things, where you can actually just say in your query, querying this data and then send it with a prompt to ChatGPT. And what I want to get back is the answer from ChatGPT. And it's quite simple and easy. I think I was a little bit fast on this slide. We see it here. We are running out of time, so just a few use cases and then question answer. Use cases, recommendation system would be another one. Other use cases, anomaly detection on time series within time series are embeddings by themselves. Document upload and document, we talk about this. Automatic classification and clustering into this. You are not limited to upfront know how many classification you have. You can change it on the fly. You can use it for massive classification. Image to text is in use cases. Tabular question answer to answer a question based on CSV table. I did it, works pretty well. Movie recommendation system, product search for e-commerce, of course, face similarity, time series, you can labeling anomaly detection on time series without heavily retraining your model all the time, and many, many more use cases. And the big thing is you don't have to retrain a model every time you're changing anything in your system. You are just storing it in a database, you're updating it, and you're deleting this data there. And yeah, here you are ready to go with vector database. I had to rush a little bit over the last use cases, which leave a little bit time for question and answering. So we are at a point now where I said, this is what I briefly want to show you. Do you have any questions? Oh, I have one. Sorry, I have the first question for you. Do you all know what is vector similarity search in a high-dimensional vector space? Maybe you can answer it in a chat.
All right, thank you for your input. We also have some questions in the chat already. If you stop sharing your screen, you can also see them for yourself, but I'm also gonna go through them. 1 second, please. I think the first question would be, how large or how many dimensions would a vector representing a word have?
How large or how many dimensions would a vector representing a word have? This actually depends, of course, on the model that you are using to create this embedding. The dimension of the vectors are usually pretty large that you have. You will nowadays use a transformer model like a bird model, for example. And there we are usually talking about a vector sizes of bird 512 is an usual size for the vector. 768 vectors is a kind of a number for transformer. Strictly depends on your model, of course, how the model is trained and how many dimension the trained model give you out. This is actually the last hidden or the hidden layer of a model that you are using for embeddings. So, but a common size for the dimension in a vector are really 500, 700. They are really, really huge dimension. I have many, many dimensions on these vectors. If you train your own word to vector model, and very old school time, but you usually don't do it nowadays, you can end up with less of this. Yeah, images is usually depends on image size and so. But yeah, they are quite big in huge in dimensions. So you are not can calculate it on your own as a human being. The similarity, you need a computer to do this. I hope this answered the question. I see there's another question. Should I just go on?
Yes, please go on. Thank you.
Yeah, there's another question I see. What would I get if there is no similar object in my search query? Will I get a nearest object even if the distance to it is huge? That's actually a very good question, Elena. Actually, this is a very good question. You could expect maybe that if the distance is huge, you of course will get an object which has nothing to do with your search query that you put in, that you actually use search for the word king, and what you get out of it is something like forest or something like this, because they have nothing to do with this. It works the way that usually you have a pre-configured distance, which is the maximum distance where it takes the object from. If it does not find an object in this distance, you will get an empty list of objects back, which is an empty array. You have to check for this then in your code. And of course, you can usually add to your query statement that you do. For example, Weaviate definitely know for this, and all the things need to have this. When you're doing the query, of course, you can also ask in the query, select every document from the database, select from a movie database, the title and the description and the review from someone and the directors. where the distance is not higher than 0.5 or something like this. And then the database will really look for object which is in the distance range of 0.5. If all the object that it found is far away than this, you get an empty list again back. And usually you do also limit it, of course, and say, when you found it, just give me the first 10 results. You usually don't want 500,000 or whatever you got there. So you can put it into the query. Ask for this. This is one way, and usually have in configuration. So no, you will not get an object which is, you can if you like, but don't make sense. Okay, I hope this answered this question. The next one is also from Elena. How can I be sure that the returned object is similar to my search? Is there any probability or uncertainty provided somehow? Yes. Again, very, very good question. Unfortunately, until next Saturday here in Glasgow talk where I really show this in practice. Maybe I will do it on the next JCOM, we will see. But it is a good question. Yeah, of course. If you are doing queries, you can ask in the query for all this metadata to get back, and you get back in your research result. Usually, for example, the distance between your search query and the object that is then returned. You can also have some depending on your query, like probabilities that it matched something. If you haven't, for example, using a query and answering model, you get also back the probability of the answer. And if this is actually an answer to this. And yes, you can get this information. You can get the distance between the object that you found to your object, and you decided on your own if this is really similar and how similar this is to your answer. You can ask for all this detailed additional information in your query, and you get it. At least Weaviate is doing it in this way. Okay, there is another thing from Ambros Barber. How Microsoft semantic kernel related to RAG? To be very fair and honest with you, I haven't looked into Microsoft semantic kernel at the moment. I will do them afterwards here. I have no idea. Maybe I have to look in it later on. Maybe you can write me an email and we'll discuss this later on. Erik Bamberg at web.de. Erik.bamberg@web.de. I will discuss this later on. It sounds like an interesting topic, Microsoft semantic kernel. I have no idea how they are related to another. I would have really look into semantic kernels inside of this. Yeah, I think this were all the domain questions. There was from Alex another question. Can we get the slides? Yeah, I would say you actually can send me everyone who is interested in the slides. Absolutely, just feel free to send me an email, and I will just send it to you. Hope it will find it. I just share my email address here on the chat. Yeah. There's another question coming up. Is there a free vector database I could check? Which one did you use? Yes, Weaviate is a free open source vector database, and I would recommend to check out Weaviate that I mentioned before. This is Weaviate. Weaviate.io, I think it is. Check this out. Mybus is also free as well. So as far as I know, I think so. Check this out, but Weaviate is a very good choice for you to use, and it's very mature, and it do a lot of the tricks that I showed you before, and had good examples on this. It is correct that one DB has to have the same number of dimensions. Otherwise, how the distance is counted is scalar. And not the DB need to have the same dimension. Every DB has kind of tables inside of this. So if you store movies, you have a collection, it's called, or a class in the database, which is a table. And usually the dimensions inside of a collection table class, however you name it, is the same, but don't have to be the same in one database instance, just in one, call it table. It have to be the same, because the model is creating the same dimension. Name a test, different the kind, but yeah.